So this first presentation is Machine Learning 101. So what you need to know about machine learning to use it. So first, you're here to talk about machine learning, but why is machine learning such popular at the moment? Because artificial intelligence, machine learning, neural networks, they are not new. They come from the 50s. And they suffered from cycles of hype, overpromise, and then disillusion. So there's several of these cycles. But now there is a new surge of machine learning. It's popular once again. So why is that? There are three main reasons. First, the data. We, all of us, produce a lot of data. We are live streaming the event, so we produce video data. I created these numerical slides. When we interact on social media, we create some data, we take pictures, and so on. So now we have a lot more available data, and it's cheap to store as well. Second point, there is an explosion of processing power, notably with GPU, graphical process unit, and distributed computing. So it's a lot easier to do some heavy processing power hungry tasks nowadays. And finally, there are some theoretical development in models and learning algorithms. And in the past 10 years, a few domains were revolutionized by deep learning. Image, speech, and video processing. You all know about Siri and Alexa and so on. They can understand when you say to them. Language translation, while still not perfect, is very good nowadays, better than before. Games playing, also, quite some big advancements. The Go, the board game, world champion Lee Sedol lost to AlphaGo in 2016. It was a very big event. And also video games like StarCraft 2, which is strategy in real-time video games with partial information. We now have a machine learning algorithm that can play at the level of professional. And finally, protein folding was also greatly advanced by machine learning techniques. But we're not here to talk about video games, sorry. We're here to talk about security. So why is machine learning can be useful for security? It can be applied to several tasks, several domains of security. Intrusion and anomaly detection, malware identification, synthetic data generation, and also for natural language processing, if you want to have a summary of system logs, to detect the spam, to analyze the website, and so on. You can also use machine learning for data mining for security, to identify community, or for analyzing an incident data. But we didn't see the revolution yet. It's yet to come. There are a lot of progress, with good progress. But while we see some commercial applications like Siri or Alexa that use speech processing based on machine learning, a lot of commercial solutions in security, like intrusion detection system and antivirus, don't use machine learning much. Okay, I use a lot of words. Machine learning, artificial intelligence, deep learning. Maybe it's time to just take a breath and just define what is it. Artificial intelligence is a very big domain in computer science, and it aims at solving complex problems. What means complex? It just means that we could not do it before artificial intelligence was born. So it can be planning with constraints, pathfinding, knowledge representation, and so on. So it's a very broad domain. Inside this domain, we have machine learning, and its goal is to use data to create a model that will do a task afterward. For example, a model that will do intrusion detection. Inside machine learning, we have deep learning. Deep learning is machine learning techniques that is based on neural networks, a special kind of models, with multiple layers. They can use a lot of data, they need a lot of processing power, but generally they get the best performances. And that's why the three reasons I gave earlier are so important, because even though neural networks are not new, now we have the data, the processing power, and some theoretical advancement to use them to their full potential. And finally, a connex domain called data mining that use machine learning techniques to explore, understand, and interpret the data. So, what is the difference between machine learning and data mining? The goal of machine learning is to create a model that will do a task. For example, detect an intrusion. So it's really creating this thing that will do a task after hand. In data mining, the goal is to extract some knowledge from data. For example, I want to understand why an accident happened. I want to know what are the commutes in this graph of relation, and so on. So the output of data mining is knowledge, while the output of machine learning is a tool to perform a task. So in this machine learning 101 course, we'll see first how to organize this toolbox of techniques in machine learning. Then I will present the steps of machine learning. I will present afterwards some families of models, because it's important to get a grasp of how it works, to really understand why it failed, for example. I will present some hurdles in machine learning, why it doesn't always work, and I will conclude. So, machine learning is not new. Since the 50s, we developed a lot of tools, and now it's a very big toolbox. But it also means that it's not easy to find what is suitable for my problem. So, there is a main way to organize this toolbox, and is to divide these techniques into problem types. More precisely, we call them learning settings, and specify what is the goal of this machine learning technique and on what data it relies on. So most techniques we will talk about are adapted for one learning setting. So it's really important when you have a problem and you think maybe machine learning can help you, need to identify what is the learning settings, so you can afterwards find the tools that can help you for that. Before presenting these settings, I will just talk a little bit about how the machine learning works in general. We generally have two phases in machine learning: the learning phases and the inference phases. In the learning phases, we use some training dataset that will be transformed with a machine learning algorithm into a model. So in the learning phase, transform some training dataset in a model. And then in the inference phase, we will use some new data and we'll use these models to make some prediction. So typically, learning a model is done once, and once you want to use your model that is learned, it's the second part, the inference phase. Now, the learning settings I talked about earlier. Well, three main settings in security. The first one is supervised learning. In supervised learning, the training set, so the data you give to the machine learning algorithm, contain a label for each instance. The label is what you seek to predict. For example, you may want to predict the number of inbound IP connection to a machine based on other data, other status of a machine. If this label is continuous, if it's a quantity, it will be called a regression task. If this label is categorical, for example, if you want to predict the family of malware, or detect whether a message is a spam or not, it will be called a classification task. Sometimes it's called detection task, there are only two possibilities, either spam or not spam, malware, not malware, and so on. So generally in security, your labels will be generally benign or attacks. And sometimes you can have some specific attacks. For example, you might want to predict whether it's a DDoS attack, if it's a worm malware, if it's a spear phishing message, and so on. With supervised learning, if you have access to data with labeled attacks, you can, for example, make an intrusion detection system, an IDS, that will detect attacks based on what it learned from your labeled data. The second learning setting is unsupervised learning, where you have no label at all in the training set. So you don't have an objective you want to predict. There's a lot of subcategories in this one. For example, outlier detection task. The goal is to identify instances that don't resemble the others. The clustering task, your goal is to group similar instances into clusters, so into groups. The dimension reduction task, when you want to reduce the size of each instance while retaining as much information as possible. And data generation task, when, based on some training data, you want to create some new data close to the first one. You probably know for this one, the website "this person doesn't exist," but invite a new face every when you go on the website. So this one is the data generation task. In unsupervised learning, sometimes there is not the learning and inference phases. For example, when you do some clustering, there is no learning phase and an inference phase. You are fused into only one phase. You give the data and its output in clusters. So in security, we usually use this task as a way to understand your data. For example, to understand what are the outliers or what are the different groups with clustering. Outlier detection can also be used in intrusion detection system. For example, if you have an homogeneous population of computers or devices that are homogeneous, so they should have the same behavior, you can use outlier detection to detect whether one particular device is doing something else. And in this case, you don't need label. It will just be because this device is not performing like the other, but it will be detected as outlier. And the third learning setting is called semi-supervised, and it's a bit of a catch-all category where you have some data, some label, but not all of them. So it can be, for example, positive enable learning, where you have some instances that are labeled, but not the others. And the goal is to label the other. It's notably the case where it's very costly to label some data, because sometimes it must be done manually. For example, if you have an incident, it can be costly or just time-consuming to label it. So in that case, we don't want to just throw to the trash every unlabeled data. So we use unlabeled data along with labeled data to make sense of it. Another task is one-class classification, where you want to do classification, whether it's, for example, normal or attack. But in your dataset, you have only an example of one class. It's typically the case if you do a behavioral intrusion detection system, when you have example of normal working system, and you want to detect whether there is an anomaly. And the last one, but not really used in security, is active learning, when the learner can ask for labels, with the objective of having less labeling as possible, as few as possible. Okay, and there are a few other learning settings. I won't talk much about them. In some cases, it could be useful. Learning to rank, the goal is to predict a ranking of a list of items. Can be used, for example, in recommendation system. Reinforcement learning, when an agent can interact with this environment, do some action and get some reward. And its goal is to understand what action to do depending on the circumstances. It's typically the case with robots that learn how to interact with environments. AlphaGo is also reinforcement learning because it can play against itself and see how well it will perform depending on the action it does. And all of our learning settings have some variance. We can do some federated learning. It's a kind of privacy preserving distributed machine learning technique. We have a talk this afternoon on that subject. Transfer learning, when we use some pre-trained model for related tasks. Few-shot learning, when the goal is to classify with as little training data as possible. And multi-label learning, when sometimes you want to affect multiple data, label to one instance. If you have a picture with a dog and a cat, you want to put both labels on them and not just one. So we saw the main categories of learning settings. Supervised means we have the label in the training data and we can use it to learn. Unsupervised means we have no label data. And semi-supervised means we have only some label, or maybe we could observe only one class. So the steps of machine learning, there are 5 of them. First, we need to collect data, because machine learning is data-driven. Then we need to prepare them. Then select the model we'll use and tune it. Afterwards, we'll train the model. And finally, we'll evaluate it. So we'll give some advice for each of these steps. So first, data collection. Typically, it will involve some experiment. So depending on the setting, if it's supervised, semi-supervised, or unsupervised, we have some label or not in the data. If you want to design an experiment, try to observe as many different phenomena as possible, to be as representative as possible. For example, if you want to study malware, try to be close to the real distribution of malware and don't work with a clear imbalance between one class and the other. Some advice: making a good dataset is difficult. Every dataset gets criticized, notably by the seed team. So reuse a public dataset when possible. It's not always possible, but if you can, it's probably the best shot for you. But if you're motivated or just don't have a choice to run some experiment, some advice: in supervised learning, try to have some balanced class. Because if you have very imbalanced class, for example, if you measured an attack far more often than another one, the learning algorithm will be biased into that one and will concentrate its effort into learning the majority classes. So a slight imbalance in the classes is not so bad, but try to avoid severe class imbalance. It will make your performance worse. And in supervised learning, try to focus on the diversity of data to get the most information out of it as possible, and try to vary the experimental settings as well, to really capture as much as possible. Okay, but what should I measure? I can't tell you, you're the expert. So I won't tell you what you should do, but I can give you some advice. The first trivial advice is try to measure anything that could be useful for the learning algorithm. And more generally, don't be shy to measure as much as possible during experiment, because it's easier afterwards to remove some data than to rerun some experiment with new features. So just try to measure anything that could help you and help the learning algorithm. Be aware that machine learning, its output will be only as accurate as its input. So in experiments, there will always be some technical or human errors. It's very, very important to pin them down and try to mitigate them, because if you have some poor quality data set, we have poor quality performances afterwards. It's especially critical if your machine learning system will do some kind of decision help. Because if it is based on previous decision, if there was some bias in the previous decision, it will just once again be biased itself because you just try to repeat what was previously done. So be careful of biased data. It will produce a biased output. Okay, we talk about a bit about experiments. Now, okay, I'll run some measures. I want to use machine learning. What is the format I need to use for machine learning algorithm? So for them, data must be structured into vector. A vector is a structure with a fixed number of what is called features. The fact that it's a fixed number, it's not really, it's a hard constraint, but it's not easy to get around that. So if you work with data with variable length, for example, if you want to study network packets, function parameters in system calls and so on, you will need to transform data to make sure that it uses in the vector the same amount of features. For example, if you work with network packet, you may want to have a big vector and fill the vectors with 0 values at the end. It's called padding, to be sure that all vectors are the same size, even though the data itself does not expand to a full vector. Another possibility is to use some descriptive features of your data. For example, to measure its mean, its variance, to measure the number of n-grams, and so on. So you're sure you can summarize the data in some fixed number of features. In machine learning, we do a difference between discrete features and continuous features. A discrete feature can take a finite number of arbitrary values, so it's categorical. Continuous features is a quantity, and generally you can use meaningful operations like addition and comparison. So as an example, if you want to create a vector from a network packet, you will select for feature. You can, for example, select the length of the packet. It will be continuous because it's a quantity. The number of occurrences on some trigram in this packet. So once again, this is continuous. Whether the source IP is public or private, there are two categories, so it's a discrete feature. And the server port, for example, 2180, this is numerical values, 21 and 80, but it's not a quantity. The value 80 could have been 100 or just 2. The value has no real meaning. So in that case, be careful, it is a discrete feature. You can convert, you have techniques to convert from continuous to discrete features and vice versa. For example, if you want to convert from discrete feature to continuous, you will use what is called a one-hot encoding. If your discrete data are, for example, 5 categories, you will create 5 features that can be either 1 or 0 depending on which is the value of a feature. If a feature's value is the second value, you can put a 1 in the second feature. You can also convert from continuous to discrete features by merging interval values into categories. So, for example, for the length of the packet, you could do just 3 categories: small packet, medium packet, and big packet. And this is notably useful because some models can only deal with either discrete or continuous data. Notably, neural networks can't work with discrete data. So we need to use some trick, like one-hot encoding, to make use of them. An important step in the machine learning process is the feature selection. I told you earlier, try to measure everything you can, and then we'll sort and we'll discard the useless features. How do we do it? two categories of techniques. The unsupervised feature selection that don't rely on the targeted label. The idea is to remove some redundant features. For example, feature with very high correlation. So we can discard one and keep the other because the ones we discarded don't bring much information to the other one. We can also remove feature with low variance. For example, if feature is almost always the same value, it doesn't bring much information. These techniques don't rely on targeted labels, so it's called unsupervised. But of course, you can use it in supervised learning. In that case, just ignore the label. There is also supervised feature selection, so you can rely on the targeted label, and then you will try to remove the irrelevant features that have no statistical connection with the label. Generally, it's an iterative process. When you get a subset of your features, you measure the performance of your model, and you will try to add or remove the features, and you will see if the model is better, its performances are better or worse. So you can try to pin down one subset of features is really useful. One important step as well is preprocessing. You probably know about that, but you should remove some duplicate values. If you have some not number values, try to replace them. If you have erroneous data because of some experimental probe issue, you should remove them. And outliers, it depends. If they are legitimate, if they are a real phenomenon, you should keep them. But if you think, okay, just a problem with the experimentation, and I think it has no real reality, you should remove them. If you have some categorical values, some categorical features with values that are really not represented, maybe one or two occurrences, should try to merge some categories to ensure to have at least some representativity for each one. Another useful preprocessing for machine learning is standardization, when you ensure that every continuous features have the same mean and same variance. And we'll see later, it's useful for distance-based model. Now, you can start into machine learning black magic. How do we select the good model? So first, you need to remember what is your learning setting. Am I doing a regression, a classification, an outlier detection? Then try to identify some particularities of your task. Are you dealing with a time series analysis? Do you want to have some explainable prediction? Is it important for you? Are you trying with some text? And based on your needs, we try to find a list of the algorithms that fits that. And then there is no magic, just try them. Generally, try to start from the simplest one. And don't overcommit to one algorithm. If you have your favorite algorithm, try the other one, because some algorithm may work very well in one setting, but not in the other. So be agile and don't be afraid to experiment with different models. And I advise you to start from the most simple models. Why is that? First, you generally need less data. So can you do it earlier, even when your experiments are not complete, for example? You can try to run some models. They're generally more robust. The performances are more consistent. And generally, they're easier to parameterize, to learn, and to interpret. So you can have a very quick iterative process when you try some simple algorithm. And then, if your performances are not good enough, you can try some more complex models, but try to start with a simple one, at least as a baseline. And maybe you will find that a simple algorithm is all you need. You will find online a lot of advice on what model should I use. It's an example from scikit-learn website. I won't describe it here. And then, how should I evaluate my model? Generally, in machine learning, we use what is called cross-validation in supervised learning setting. The idea is to use 90% of the data set to learn a model and 10% to evaluate it. And you do it 10 times, so you evaluate on all the data set. It's not always possible, it depends. For example, you could say that no, I can't use newer data to predict some older data. I need to preserve the time, for example. But it's a good starting point. Validation metrics, you probably know already them. I won't insist on it. They depend on the task. In classification, we generally try to get the confusion metrics. There are some more dedicated metrics, for example, intrusion detection, when you have recall, precision, F1 score, and so on. In detection, so binary classification, you can use work analysis and the area under curve. And in regression, what we usually use in the mean square error. And finally, you will try your models and you will have some errors. And that's the difficult part. Where the error comes from. So first, if you use an explainable model like decision tree, we'll talk about that later, you can just try to read it and see if it makes sense for you. Because you are the expert, you should know how it works. So you can just verify whether it seems legitimate, it seems good. And you can also analyze some errors. And you will have a lot of possibilities for why is there an error. Maybe it's an edge case and you don't have enough data on it. So maybe you should run experiments on this edge case to better learn it. Maybe your model, because of how it works, just can't represent the reality. Sometimes the problem lies in the evaluation score. Maybe for you, not all errors has the same weight. And maybe it's just an edge case that you don't need to fix. We'll talk about that later, but generally, if you want to add some particular rules to fix all the small errors, we just end up with a worse detector. And finally, maybe the detector can't, for example, set two categories of attacks apart because it lacks some information. There is some missing features, and you, as expert, you should see how maybe bringing that information to the model can help it to differentiate these two cases. There is a new trend in machine learning called AutoML, which is, okay, why do we need an expert? You can just give it to a machine algorithm to tell you what algorithm you should use. So, how to automate the automation. So the goal is to simplify multiple steps of this machine learning pipeline, data preparation, feature selection, and model selection. And the goal is to bring machine learning to non-experts. And even for experts, it can be useful to have some baseline to build upon. It's a relative new domain of research. There are already some implementation. For example, in the open source world, you have AutoScikit-learn, MLBox, and Teapot. And in the GAFAM, you have Google Cloud AutoML, AutoGluon from Amazon, and Azure Machine Learning. Now I'll present a few models of machine learning. It's important to understand, to have an intuitive idea of how they understand, to understand after why they fail in some cases. So we start with the simple one and go to the more complex one. KNN for K nearest neighbors. Its idea is to predict the class of an instance. You check the closest instances in your training set. And in your training set, you check what is the class for them. If you want, for example, to detect whether it's a spam or not, you check close related mails and you verify whether these mails were spam or not. Generally, you get good performances, and it's relatively easy to understand the prediction because you can just check, okay, for this email, for example, what are the neighbors, and you can verify whether where does the problem come from. it's generally used with continuous features, and in that case, you should normalize the features. Otherwise, it won't work. In some other variation, you can vote. The vote can be weighted by the distance. So I seek my nearest neighbors, and if my the neighbor that is the nearest to me has a bigger weight on the vote than someone that is a bit further. So you will check the k nearest neighbors. It's not easy to find the good k value, but a good starting point is to use the square root of your training set. There is a variation of this algorithm called LOF. It is based on the local uncertainty and can be used for outlier detection. The idea is if a point is in a low density area, it is probably an outlier. So an example for this one. So the point here is the training data set, and the color here are the prediction. For example, if I'm here, the prediction will be light blue. We can check, for example, why here I am predicted as orange is because my close neighbors are orange. So it's quite intuitive to understand why there is a color for each one. Sorry, the color are not very good on the screen. Another model is called naive Bayes. It's used for supervised learning, and the idea is to modelize the distribution of the features for each class. For example, for attack 1, we will see this kind of value for the features. For attack 2, we will see this kind of distribution for the values for the features, and so on. It's not very good in terms of performances because statistically it makes some big assumption. But I wanted to tell you about it because it has one interesting capability. For each class, it will give you a probability. But for example, if the detector this probability don't sum to 1, so for example, it can say to you, for all the classes, I think the probability is low. So maybe, I don't know, maybe it's a new class. It can also say to you, okay, the probability for this class is 90% and the probability for this class is 70%. So the sum is not equal to 1, and so you can know how certain the model is, how confident it is in its prediction. And another good thing is that it's very easy to interpret, and it can work in embedded system very easily because of very low time and space complexity. Decision tree is another model. It's very famous. The idea is to have a set of rules in the form of a tree, and each node will contain a simple rule, like the value of A is value 1, or B is greater than 0.5. Here's an example. So the root is here. It will check the flag features, and depending on this value, it will go to one branch or another. For example, if the flag is S0, it will predict, okay, it's a DOS attack. If the flag is RSTR, I can't say for sure, so I will verify what is the value of source byte, and so on. So this model is very easy to interpret. You just need to see what branch has been taken for prediction. It has not the best performances. Depending on the implementation, it can handle continuous features or not. A good point is that it works with little data, and it is robust to irrelevant or redundant features. Random forest works as follows. It's a bunch of decision trees that was learned with random subset of the data set, so they are not all the same. And to do a prediction, you will just give some instance to all the trees, and do a voting system. So it has very higher performances, very good performances, but it's more difficult to interpret because you can have 200 decision trees, and it's not easy to check all of them. Can also be used to estimate the relevance of features. And there is a variation. If you are doing outlier detection, it's called isolation forest. We are now getting to a more complex model. SVM is a super vector machine. So originally it was a way to separate two classes with one linear separator. So if it's in a plane, the separator will be a line. If it's a space, the separator will be a plan, and so on. So it was a pretty simple model. But we have some mad mathematician that said, oh, okay, if you change just a little bit this formula with what is called the kernel trick, you can change how it works. The algorithm is still the same. You change just the computation, and you will get some more complex shape. So it's high performance model, but it's very difficult to interpret. Originally, it worked only for two classes, but now it can work with any number of classes you want. Normalization of feature is necessary, and there is a variation if you have only one class. So it's useful for anomaly detection, for example. So here is an example. So you can see the shape for each class, but I can't tell you why here is it red. I don't know. The computation says so, but why in KNN I can tell you, okay, because of the neighbors. Here I can't interpret why is there some red here and here. And neural networks are really famous. It could deserve a talk for itself, but I will keep it short. The idea is you have one neuron that does some really simple computation, some addition, multiplication, that's all, generally. And neurons are arranged in layers, and there are multiple layers, and the output of layer n is the input to layer n plus 1. And generally, it will output some continuous numbers for the regression task or the probability distribution if you do a classification task. Generally, it works the best if you have the time and the expertise to tune it. That's the real difficulty. It can crunch gigabytes of data, but if you have enough processing power and enough data, of course, it is robust to relevant and redundant features, so feature selection is not very important here. But it's very hard to interpret why I got this prediction. There are some techniques, but really not easy to use. It only works with continuous features, so you need to transform your discrete features into continuous one. And there are a lot of variations. I will talk about just two of them. Autoencoder can be used for one-class classification and for dimension reduction. And variational autoencoder and generative adversarial networks are used for data generation. So I talked earlier about the website, this person doesn't exist. They use neural network. And finally, a technique called Ensemble techniques. The idea is to use multiple simple models together to create a more complex one. There are three sub-techniques here. First one, bagging, is I use several times the same base model, but on random subset of the data. You should remind you something because random forest is based on this technique. You just use a lot of decision tree on random subset of the data and do some vote at the end. There is also boosting. The idea of boosting is you use a simple model. It will have some errors, and we use afterwards a model to deal with these errors specifically. You will get a better detector, but you will get errors, so we get a new model to deal with them. It can work. Generally, it works well, but not always. AdaBoost and XGBoost are are really a classical example for this one. And finally, stacking, when you have multiple different models, decision tree, KNN, naive Bayes, and so on. They are trained on the whole dataset, and when they make a prediction, you learn how to weight each prediction to make a global prediction. So it's like using a lot of not so good experts, but each will give you a different answers, and you will try to understand, okay, when this one is wrong, this one should not be trusted either, but when this one says that, and so on. So you can learn how to fuse their prediction to make a better one. So, as I said, random forest, a popular example of bagging. Generally, these techniques lower the explainability because you have a lot of models and it's not as easy to understand why the prediction was made. And they are not always worth the hassle. Sometimes it's more better, sometimes it's worse. So it's not easy to use. So we saw a lot of models. And I will talk a little bit about the hurdles you can face in machine learning. First, a bit of theory of machine learning. Why is it so difficult to find a good model? Why don't we have yet some good model you can use? Why sometimes they work, sometimes they don't? Why is that? In the end, a model is a way to simplify the reality. A model could be created by hand by an expert, or it could be created thanks to the specification of the system. Or, in machine learning, it is inferred from data. So, in machine learning, a model is learned with what is called a learning algorithm that takes the training data and outputs a model. It will work within what is called a model class, which is the set of models we search into. For example, the SVM is one model, and the set of SVM is what is called the model class of SVM. Usually, you have a model. For example, a decision tree, it's a model. Naive Bayes probabilities are a model. But you sometimes have techniques that don't explicitly add a model. For example, KNN, it checks the training data directly. So we don't have an intermediate model in this case. So why is there error in machine learning? There are two main reasons, two sources of error in the model. What is called the bias and what is called variance. So we do here just some regression because it's very simple to output. We have some true data. It's a sinusoid. It's in orange here. We will get some data points in blue. You can see there is some noise. It's not really on the curve, but a bit around it. And the bias is the distance between the reality and the closest model in the model class. For example, with a straight line, you can't approximate a sinusoid. It's not that we didn't find the good one. We know it's impossible. It's just a straight line. So this model class, the model class of the straight lines, has high bias because it just can't express the reality. It's just not possible. If you take some fourth degree polynomial, you can see it's here, it's blue. You can get pretty close to the real value, to the real curve. Of course, it's not exactly the same because it's a sinusoid and you can't approximate it with a polynomial. But it's really close. So its bias here is low because it can approximate the reality. So this is the bias. Then the second one, the variance. Variance is the sensitivity of the model to the training data. So here you have a 4th degree polynomial. Here you have a 14th degree polynomial. If I get some new data, we find that the 4th degree polynomial, it changes a little bit, but not so much. The blue curve is almost the same. However, in this case, for 14th degree polynomial, the curve did change a lot between the two of them. So the top one has a low sensitivity, so it has a low variance, but the bottom one has a high sensitivity, so it has a high variance. Remark here that this one has a low bias. It could fit pretty closely the curve. It could do it, but it is sensitive to the data. So it has a low bias, but a high variance. Okay, sorry about the theoretical part, but now, okay, why did I say that? What are the implications, the concrete implications of that? First, when you use simple model, generally we have a high bias and a low variance. It means that they are generally good at generalizing the properties due to the Occam-Razor principle. However, complex models have a low bias but higher variance. So they can fit closely the dataset, but they have some struggle with generalization. Ensemble technique that we saw earlier, they generally reduce the variance and the bias of the models. These two kinds of error, bias and variance, lead to two kinds of problem, what is called underfitting, it was called overfitting. Underfitting is when your error comes mainly from the bias. It's just that your model can't represent reality, it's just not complex enough. In that case, you should experiment with a more complex model. It's, for example, for that reason that they behave so poorly. It makes some assumption, so it means that it just can't be close to the real distribution. But you have also overfitting problem, where your error comes from the variance. It means that your generalization capability is poor, and how can we see it, really? You can, in this case, the performances of the test set will be lower than the performances of the training set. You will generally call there is overfitting when the model learns by heart the training set. So it's very good on what it learned upon, but it's very bad at generalizing to new data. Okay, underfitting is not really a problem because we will generally understand that, okay, this model is not good enough, I will take a more complex one. But overfitting is more difficult to reduce, so here are a lot of tips on how can I decrease the overfitting of my model. First, try to decrease the number of learnable parameters. In neural networks, for example, remove a layer, if you can. In neural networks, there are also a special kind of layer called dropout. I won't explain how it works, but its point is to reduce overfitting. And in your using an autoencoder, maybe try to use a variational autoencoder one. For other model class, for example, in KNN, the K parameter controls the bias and variance. So if you want to have, if you have overfitting with KNN, you should lower the K value. And if you have underfitting, you should increase it. In statistical model like Bayesian network, there are some score, for example, BIC or AIC, that are designed to limit overfitting. In decision tree, try, for example, to limit the maximal depth of the tree. And in ensemble techniques, try to reduce the number of Bayes models. For example, Unsupervised use less decision trees. And finally, overfitting can also happen when you tweak a lot your models. I said earlier, when you have an error, sometimes you just need to accept it and not try to tweak every bit of your model to just be good on that one, because, okay, you will be good on the training set, but you will generally lower the capability to generalize, and you will have a worse performance in the end. Another hurdle in machine learning is the security of machine learning, because now that we can use machine learning for security, it opens a new attack surface for the attackers. And machine learning can be attacked in a lot of ways. The training data could be modified. We could evade some classification with some adversarial examples. We can also have privacy loss with specific attacks, also intellectual property loss, and so on. I won't talk about it now because this is the subject of the different talk later this afternoon. So we get to the end of this part. So some takeaways for you. So machine learning didn't revolutionize security yet, but it can still help you. First thing to do is to check what is your learning setting. It will help you to identify what technique you can use. Don't forget that machine learning needs good quality data, so start looking for a dataset that exists or expect to run experiments. Take your time to design your experiment and take your time to inspect the data as well to understand them. Don't focus on one model that you know. You should be agile and try a lot of different models and start from the simple one. Maybe you will just see that, okay, I don't need machine learning for my problem because just some easy rule or another technique can use it, can do it. Understanding how the model works will help you to understand why and when they can fail. Overfitting is a risk. You need to know how to recognize. So when the performance is lower on the test set than on the training set. And know how to tackle this problem. And finally, machine learning requires a lot of trials and error, so don't use hope and tweak a lot. How to get started? There are softwares to use machine learning without programming, for example, Orange and Weka. If you want to program over 3 main languages, Python, R, and MATLAB, but the most popular one is Python, by far. Python are very good libraries. For general machine learning, we have scikit-learn. About every example you saw was done with scikit-learn. We have some good deep learning libraries as well, with Piano, TensorFlow, PyTorch, Keras, and so on. And some good libraries to manipulate data and visualize. So we'll have coffee break soon, but afterwards we do some practical exercise and we'll use the Orange software. Thank you.